Okay, so in this video, I just wanted to go through question 3 and question 4 of the homework that you had. And these were more typical of chapter 22 and 23, really, because you had types of reactions in there as well. But the first thing it asks you, what's a secondary alcohol? Well, a secondary alcohol, the carbon attached to the OH group is directly attached to 2 other carbons. That's what we said. And we had a graph paper, so if I was drawing that graph there, I'd have boiling point here on the y-axis with degrees Celsius, don't forget that, and put number of carbons on the x-axis there and plot your 6 points. Okay, and you can see that as the number of carbons increases, then the boiling point also increases. That would be the general trend. Now in part 3, they asked you to explain that trend. Now, lads, be careful, right? All of those compounds there in the table are alcohols. So you do not start talking about the fact that alcohols can hydrogen bond. All of those alcohols have an OH group. So all of those alcohols can hydrogen bond. You only talk about the type of intermolecular force when you're comparing one homologous series with another. So say if they ask you to explain the difference in boiling point between butane and butanol, okay? But here, all of these compounds are alcohols. So what they're asking you to explain here is why, as you increase the number of carbons, does the boiling point increase? So what's happening there really, going from methanol to ethanol to propanol to butanol, is the CH. They all have the OH, you see. They all have that. But it's the CH portion of the alcohols that are getting bigger or getting longer. And what did we say about that again? So like, as the CH portion increases, this is the non-polar alkyl or CH region of the alcohol. And as that gets bigger, then what can happen here is that you have stronger van der Waals between butanol molecules than you would have between ethanol or methanol molecules. Because you have more carbons and hydrogens, you have more electrons. Because you have more atoms, you have more electrons. And because you have more electrons, then you have stronger temporary dipoles, which will result in stronger van der Waals between the non-polar bit of the alcohol molecules. So you must talk about increasing number of carbons, make more atoms present, more electrons present, therefore you have stronger van der Waals, because this is non-polar. Remember, it is van der Waals forces you'll have between non-polar bits of the alcohol molecule. Yes, you can have hydrogen bonding between the OH of one alcohol and the OH of the other alcohol, but what's happening here, you see, that's the same in all of the compounds in the table. But why is the boiling point increasing as the number of carbons increases? That's the non-polar bit that you'll have to talk about there, okay? Now, then it says for part 4 to predict predict the boiling point of the next alcohol. Now, the next alcohol, of course, will be pentanol. Now, there's roughly 16 degrees of a difference between say, propan-2-ol and butan-2-ol. So if you added 16 degrees onto 99 there, you'd be getting something like 115 or whatever. So that sort of a thing, is what they'd be looking for there, okay? So just add on 16 degrees is roughly the difference between the boiling point of propan-2-ol and butanol. So add that difference on again, okay, for pentanol. Now, what's the next bit there now? Sorry. Oh yeah, so part B then says, consider the oxidation of alcohols. Now, lads, there is no carbon-carbon bonds broken. So, like, they're oxidizing butan-1-ol. So if there's no carbon bonds broken, you have to stick with 4 carbons in a row, do you know? So if you oxidize the alcohol, what possible products could you get? You can get butanal, and further oxidation of that makes butanoic acid. So butanal and butanoic acid is your answer there. Draw the structure of the organic product when butan-2-ol is oxidized in this way. Now, remember, butan-2-ol is a secondary alcohol. And when we oxidize a secondary alcohol, we in fact get a ketone. Do you remember that? So butan-2-ol would form butan-ON. And when you're drawing butan-ON, then you have 4 carbons And remember, the functional group of a ketone is C double bond O. Sorry, that was wrong. We've got C double bond O is a functional group of a ketone. So there's your butane ON. That would be what would be formed there for part 2. And then it says 3 then says clearly identify which bonds are in butane 2-ol are broken. Now, if I just draw out butane 2-ol there for a second, okay? So there's my OH, say. Now, but, remember, implies 4, doesn't it? So, like, let me just draw it there now. First, okay? Now, butane 2-ol. Is this a secondary alcohol? Let's just run through that. The carbon attached to the OH is attached to 2 other carbons directly. So, yes, it is a secondary alcohol. So, that's your butane 2-ol. Right, now, what are they actually asking you again? Sorry, now. Clearly identify which bonds are broken. So when you oxidize butane 2-ol to butane ON, what are you going to break? Well, you're definitely going to break the OH, aren't you? Because you don't want the OH functional group. It's not an alcohol. It's a ketone. And do you notice as well when I drew it earlier, you don't have this either. So you're going to have to break the OH and you're going to have to break the CH. You will actually leave that bond there between the C and the O. Okay, and now I know they didn't ask you this, but what bond would you have to make? You'd have to make the pi bond of the C double bond O, wouldn't you, if they asked you for that, but they didn't. So just to answer the question now, sorry, which bonds are broken? The OH bond and the CH bond is broken when you're going from butane 2-ol to butane ON, okay? Now, part C of that question then asks you about the ester formed from methanol and propanoic acid. Now, propanoic acid is 3, okay? So there's my 3 carbon, double bond O, the O, and methanol is just the 1. So that ester would be called what? Asterisk the carbon that came from the acid. So it's propan OH, and what's in front? What's in front here? Methyl. So it's a methyl propanoic. Now, they didn't actually ask you to name it. They asked you to draw it, and I have it drawn there. Part 2 then says, to how many carbon atoms in a molecule of this ester are tetrahedrally bonded? Well, that's tetrahedrally bonded, that carbon and that carbon, so 3. Remember, what does tetrahedrally bonded carbon mean again? 4 single bonds. How would we describe this carbon? That carbon is planar, isn't it? And then finally, they asked you for the products of the hydrolysis of the ester with sodium hydroxide. Now, remember, when you hydrolyze an ester in the presence of a base like sodium hydroxide, you get back the alcohol. So you'll get back the methanol. You don't get back the propanoic acid, but instead you get the sodium salt. Do you remember that for making the soap? So you'd get sodium propanoate and methanol. Lads, will you please remember to read your questions really carefully. If it's name, you know, what are the products, or name the product, something like that, then you need to give out the actual name, okay? Now, question 4 there then is the next question there. You're asked draw the structures to show all of the bonds in molecules B and C. So molecule B is propanol. Now, prop, remember, implies 3, it's propan 1-ol, sorry. So H. Now, lads, if they ask you to show all of the bonds like they did in that question there, I'd be inclined to show the bond, you know, between the oxygen and the hydrogen and the OH. I'm normally in school, I'm inclined to write like OH next to that, but if they ask you to show all of the bonds, I'd be inclined to extend that out, you know. And C is propanal. So when you're drawing propanal, remember the functional group of an aldehyde is the C double bond O and a H, okay? So there's my C, that's my C, and that's my B, and they're drawn out to show all of the bonds, okay? Which one of the 4 compounds that you have there contains only 1 tetrahedrally bonded carbon? Now we've these drawn, so we may as well address this first. So this is tetrahedral, this is tetrahedral, this is tetrahedral. So there's clearly 3 there. Tetrahedral, so there's clearly 3 there. Or sorry, 2, 1, 2. That's planar, of course. So B or C is not correct. Butane would be like that. So you would have 4 tetrahedrally bonded there for A, for butane. Now, if I was to draw ethanoic acid, showing all of the bonds, be like that. Now, there's 1 planar, there's 1 tetrahedral carbon. So my answer there for that question, which of the 4 compounds contains only 1 tetrahedral bonded carbon atom, then it would be D. My answer is D. B then asks you for the definition of structural isomers, so that would be fine. They're compounds of the same molecular formula but a different structure. And what is a primary alcohol? The carbon attached to the OH is directly attached to just one other carbon, okay? C and D, it says, are structural isomers, so they want you to draw, so they want an isomer of C. What was C again? Sorry. Now. So C was propanal, so they want you to identify an isomer and draw it actually, an isomer for that. Now, al. So al, the isomers that you would best associate with the aldehydes would be the ketones, okay? So let's see if propanoan would be a suitable isomer. So let's just quickly, I'm just going to sketch out propanal there. So the molecular formula for propanal will be C3H, 1, 2, 3, 4, 5, 6, and an O. Now if I'm to draw propanoan, 3, 4, 5, 6, and an O. So to be the same, it's the same molecular formula, different structure. So if they're looking for an isomer of aldehydes, you're looking at ketones, okay? So try to remember that if you can. So there's your isomer there, propanoan, okay? And we've drawn it out. Now the next thing they've asked us to do there then is to give the UPAC name for that. That's propanone. So that's fine. Now C then says, explain clearly why the boiling point of propanal, the boiling point of propanal is 58 degrees, they tell you. Why is it so much higher than the boiling point of butane? Now lads, do you see the way that, sorry, I'm looking at the MRs, sorry. The boiling point of propanal is roughly 50 degrees there it's saying, whereas the boiling point of butane is -1, say, degrees Celsius. Now, 50, why are they giving me the MR of 58? So similar relative molecular masses, same relative molecular masses. So the relative molecular mass is not the issue here to help us to explain the difference in boiling point. Here we're comparing different homologous series. So how you're going to explain the difference in boiling point is you're going to talk about the type of intermolecular force here, okay? What kind of intermolecular forces can we have between molecules of propanal? Dipole forces. Between butanes, we can have van der Waals. And you're going to say that dipole forces are stronger than van der Waals forces, and therefore to break those dipole forces you need more energy. So the boiling point of propanal would be higher than the boiling point of butane. Remember, if you have a molecule of propanal, I'm just going to call it, we'll just draw it out there again for a second. There is a polar bond. There's the polar bond, the slightly negative oxygen, the slightly positive carbon. That's allowing for dipole forces between one molecule of propanal and the next. And those forces are stronger than van der Waals, and therefore they're going to be harder to break. So the aldehyde will have a higher boiling point than the alkane. So remember, if you're comparing families, and you're talking about corresponding molecules, in other words, they have relatively similar relative molecular masses, then you must talk about the different type of intermolecular force there, okay? In the second part of part C, then they've asked you to explain the difference in boiling point between ethanoic acid, which had a boiling point like of 119 degrees, and propanol, which has a boiling point of 98. Now, with the alcohol, you have hydrogen bonding, okay? And with the ethanoic acid, you have hydrogen bonding. But remember the difference. With ethanoic acid, okay, you can actually have, remember we were drawing this out in the previous thing. This is slightly positive, slightly negative, slightly negative, slightly positive, slightly negative, slightly positive, slightly negative, slightly positive. So look at what you can have. Between the slightly negative hydrogen of one acid and the slightly negative oxygen, there's the hydrogen bond, but there's one too. So you'd have to mention dimers. Dimers are possible between molecules of carboxylic acids. So what does a dimer mean again? 2 hydrogen bonds per molecule of acid. Whereas with the alcohol, there's only 1 hydrogen bond between one alcohol molecule and the next. So the fact that you have 2 hydrogen bonds to break between acid molecules means that acid will have higher boiling points. So the mention of dimers and explain that. Part D then says there, what's the organic product reaction C? What was C again now? C was propanal. Now, lads, this comes up quite a lot actually, to distinguish between aldehydes and ketones. Do you remember the three tests? Acidified KMNO4, then you had the ammoniacal silver nitrate and the Fehling's solution. So you can further oxidize an propanal to propanoic acid. So if you put, this is a good oxidizing agent, KMNO4. Fehling's is an oxidizing agent. The silver ions will be oxidized to pure silver metal. Remember, the oxidizing agent is itself reduced. So the Mn+7 goes to Mn+2. Now, they didn't ask you for an observation there, but if you did add propanal to acidified KMNO4 and warm it or heat it in a test tube of boiling water, then you would observe purple going colourless, because you will reduce the oxidizing agent, you will oxidize the propanal to propanoic acid, okay? Remember, ketones will not oxidize further, so therefore if you put a ketone in with acidified KMNO4, you won't see any difference in colour, okay? Lastly, then they asked you to write between the alcohol propanol, okay, and sodium, wasn't it? So that again, that comes up a lot here. So here the alcohol is actually behaving as an acid, remember? Okay, so sorry, now I put the wrong thing in there. So behaving as an acid, so it'll donate that proton. So you'll have C3H7O minus, so the Na attaches on there, doesn't it? And then so you'll have that, and then you'll have plus a half hydrogen, okay, because that's one H coming off there. So one hydrogen atom, half of H2. Remember that hydrogen is diatomic, okay? So that's the reaction of metals like sodium with alcohols behaving as an acid, and they donate the proton like that. Sodium ethoxide.